Hi, I'm Anshul Singhvi from Bard College at Simon's Rock. This research was done under Professor Harold Hastings with collaboration from the Magnus Lab at Vassar University. We present a simple neural model which describes the undulatory motion of a small worm. In simulation, we show that this simple model can replicate complex locomotion, and this implies that the model can be scaled up to more complex neural circuits. I'm going to give is sort of at the intersection of dynamics and biology. So, I guess I'll start from the top. C. elegans is a small, around 1 millimeter long nematode. It's this really heavily studied model organism. So we know its entire neuron map, all the connections of the neurons, how they connect, the connection strengths, and so that's what they call the connectome. And there's a large literature base for it as well. There's like a bunch of websites and stuff. This is a C. elegans swimming. So this is actually taken from our collaborators' lab. They've done shadow imaging, so you project a laser onto a screen and the C. elegans swims in front of the laser. And you can see it's sort of undulatory, right? And it's not exactly what you'd expect an optical swimming to look like. But so we started to say, can we make a very simple model of this undulatory locomotion? We know it's connectome. So the question we had was, can we generate its motion with a very, very simplified version of that connectome and a very, very simple neuron model, just two differential equations really. So what we did was we created a system of ODEs, which sort of simulates each neuron. And we also implemented an analog realization of the system on circuit. So this is, I can't see it. There's something called the central pattern generator up here. It's essentially a small neural circuit which serves as the regulator of motion. So this doesn't just exist in C. elegans, it exists in a bunch of other animals as well. So at the top here is what they call the head oscillator, which is essentially a pair of neurons at the head of the worm, which then drive what they call a descending pathway of neurons. Each neuron then drives some body wall muscles or motor neurons or what have you. So here I've sort of represented this as a graph. So you've got each node as a neuron. The arrows represent excitatory sort of stimulus or diffusion. You can also think of it as a gap junction. These two represent inhibitory diffusion. So that's, if you know neurodynamics, you might be familiar with this. This is the system we used as a neuron model. So the Fitzhugh-Nagumo system is one of the simplest biomimetic neuron models. There's a fast voltage variable, V, and there's a slow sort of inhibitor gating variable which stands in for potassium current, which is W. Epsilon, A, and I external and B are all constants. Now, the interesting thing you can do with this is you can add on a coupling term, which essentially simulates sort of diffusion between neurons. So you just add some diffusion constant, which can be positive for excitatory or negative for inhibitory, times the maximum 0 or the difference in voltage between the neurons. We found that was a reasonable way of simulating it. Right, so we'll talk about that. So these are the sort of dynamical modes of Fitzhugh-Nagumo. The blue curve is the V null line. You may not be familiar with that. It's essentially when the derivative of V is 0. So if I go back, this function here, dv v cubed over 3 minus v plus minus w plus I external. So the blue is when that's 0. The red is when w is 0. And so here so the derivative of v sort of takes you towards the right below the null line and to the left above the null line. So just to go over the dynamics of it, in the excitable regime, if you give an impulse to the neuron, what will happen is it'll go over one cycle and then collapse back into a steady state over here. But if you're in the oscillatory regime, what ends up happening is let's say you start off over here, you essentially just keep going in a cycle. So sorry about this pixelation, it was from a paper which also was pixelated. But this one is the real C. elegans null lines. I think Shu et al. And Hinas had measured it. So the red one is the V naught line, and the blue one is the W naught line, essentially. Sorry about the different color schemes, but again. So this model is Morris-Lecard. It's sort of a middle ground between the real one and the simulated thing we have, which is Fitzhugh-Nagumo. You'll notice that in both of these, there's sort of a slight curve on the W naught line, which we don't have in Fitzhugh-Nagumo. It turns out that doesn't really make a difference. All you need is a spiking neuron. And so for the simulation, again, generalized diffusion coupled ODEs, neurons as graph. So this is the code we use to simulate. It's really simple. All you have to do is solve a bunch of differential equations. And even the equations are not that hard. We start with some initial conditions, a couple of parameters here, return an array, and we used, I think, SciPy's ODE integrator, just the standard one. So we put this worm has its head tethered. We essentially took the output of our neural simulation and plugged it through a bunch of filters to simulate muscles and muscle movement. So that was the simulated worm. This, I'm just showing for emphasis, is the real worm. And you'll notice that they're pretty similar. Of course, the head of the simulated worm here is anchored because we haven't gone into the real physical simulation or feedback yet. But essentially, you can think of, if this worm is slightly constrained by the water, right, that it's swimming in, you can think of this worm of the simulated worm as entirely unconstrained. So it's a pretty decent model for how simple it is. So in the I think this was maybe the 70s, Shinichi Nagumo and a couple of collaborators proposed a circuit which used tunnel diodes and inductors to essentially simulate the Fitzhugh-Nagumo equations. Jim Keener simplified this by replacing the tunnel diode of the inductor with some operational amplifiers. We implemented the diffusive coupling with resistors, followers, and inverting amps were needed. And so here we've got some circuit diagrams. This is the tunnel diode that Nagumo used. In our circuit, which is a small modification of Keener's, we've replaced that with an op-amp, which essentially slews to saturation. So if I go back, never mind, sorry. If I go here, this blue thing is the Nagumo V naught line, which is essentially cubic. We've replaced that with a piecewise linear approximation. So that's how this functions. And we've replaced the inductor that Nagumo had with just an op-amp integrator. So they essentially do the same thing. And as you can see, it's a pretty simple circuit. I mean, theoretically, you could replace some of the op-amps with transistors, make it even simpler. So I've put up here some graphs that we got with the simulation. So this is with a positive diffusion coefficient. This is two neurons coupled with a positive diffusion coefficient, two neurons coupled with a negative diffusion coefficient. And this is what we got from the circuit. So a lot of the noise you see here is just from the oscilloscope or electronic noise. But they're pretty similar. And you can actually, on the positive one, you can change the phase difference between. So each line here is a separate neuron's voltage. So you can change the phase difference in the neurons based on the diffusion coefficient. It actually turns out this is pretty annoying to do when you have so the resistance is inversely proportional to the actual diffusion coefficient, so it's pretty sensitive. But yeah, so I think I actually am 2 minutes fast.
Great.
But so it turns out we can simulate C. elegans with a minimal central pattern generator. It's computationally cheap. It translates to a simple analog circuit, and it's surprisingly similar to the real unconstrained motion. So some of the next steps we were sort of thinking of were, it would be great if we could incorporate feedback from sensory neurons into this, but we're not really sure how to do that yet. Another interesting thing is to see if we can fit our model to an actual worm. So we've got data of essentially image segmentation data from several worms, so you track segments of the worm. So it'd be interesting to see if you can sort of play around with parameters, maybe add a couple of layers of post-processing to replicate an actual worm's motion. So yeah, that's it.
Okay, sure. So, so you have a nice circuit that's doing this neural thing.
Could you connect that to a servo, or maybe a string of servos together with stringers and make a mechanical one?
So you could, and actually a couple of people created a mechanical one which was just programmed, so you had, they defined some curvature for each segment and so on. So we could actually do that.
Yeah, it'd be nice to have a
That
biologically
would definitely be
inspired
interesting.
mechanical one.
I guess for the circuit, why did you use a linear approximation rather than a cubic approximation?
So the tunnel diode that Nagumo used is extremely expensive and was only manufactured during Cold War. So, so that's a little bit of a problem.
Please. I've got a question, obviously. So one of the things I'm interested in is that kind of you've managed to kind of map a specific behaviour to a given ODE.
Right.
And that's kind of, in some sense, it's not surprising that you should be able to do that.
Sure.
ODEs are tremendously flexible and you just tell this is what I want to do. But given you've got the whole connectome now, this nematode one, could you envisage a way of kind of building this and adding other kind of at least experimentally observable behaviours of the nematode and kind of incorporating that into
Right, so that would be one of the next steps. It's sort of interesting because this is a really simple model which generates a realistic undulation.
Mm-hmm.
But the problem is, as you try and add more and more things, you may stray further from the real one, because now you no longer have that nice mathematical approximation. So, for example, if I try, what we've done here is we essentially used a couple of cubic filters to simulate muscle motion. But if I tried to actually get the dynamics of a motor neuron, a muscle, and actually simulate those, it would be less trivial, shall we say.
Yeah.
But it's definitely an interesting idea and something we're looking into.
Okay. Well, any other questions? Let's take Anshul. Okay. So, this is the point where I have no idea who's